Hi everybody, welcome back. So today is the sixth session of chemical kinetics, and the topic that we are going to discuss today would be kinetics of second order reactions. And if time allows, let's complete kinetics of third order reactions as well. Okay, now before writing the heading, let's go back and discuss the solution to the homework question that we had. So the question was plotting a graph for ln A by A0 versus T for a first order reaction, which was asked in June 2014. There were four options, statement type options, and the correct answer to this question is, so we already did a variation of this, okay, and we got a straight line which passes through the origin and it has got a positive slope. Do not think that question number 15 and 16 are the same. If you have marked option A, that is a straight line with positive slope passing through the origin, that's wrong. That is wrong. Why? Because look at the parameter that is plotted along Y. Here it was ln of A naught by A. Here it is ln of A by A naught. That is the difference. Okay, so we have to rearrange the equation in such a way that we get this parameter as the y-axis. Let's try it out. So what do we get? We already know that ln of A naught by A is equal to KT. This is the integrated rate equation for first order kinetics. This was already taken that if you have ln x is equal to y, and if I take a reciprocal over here, like ln 1 by x, this will become minus y. General mathematics. So if I do the same, okay, because in the question they have asked A by A naught, correct? They have asked A by A naught. So let's take the reciprocal. We get ln of A by A naught. I have taken the reciprocal. So here we'll get minus KT. Now, if we plot a graph, now our equation is of the form, this is y, this is x, and we have a negative slope. There is no intercept. So intercept is equal to 0, and we have a negative slope. Correct? So the correct answer is going to be, this is of the form y is equal to mx, which is a representation of a straight line. So it's going to be a straight line with negative slope passing through the origin. Option B is the correct answer. How would the plot look like? How would the plot look like? So as the slope is negative and it passes through the origin, it comes like this. Okay, so along the y-axis, we have ln A by A naught. And along the x-axis, we have time. We need to have a straight line with a negative slope. What is the slope? Minus k. And what is the intercept? C is equal to 0. So this is how the graph will look like. And the correct answer is option B, not A. Okay? It is B, not A. Okay. Now, just a shortcut. Now, for zero order reaction, I had already mentioned, please do not take this down. I had already explained under zero order reactions that if you start with 100, now this is for zero order reactions, okay? If you start with 100, for some particular time t, if there was a drop of 20 units, let's say, it becomes 80. And if the same time is given to the system, to the chemical reaction, for the same period of time, same amount of the reactant will drop again. It will come to 60. And then in the next t minutes or t seconds, whatever it is, for the same time, again, the same amount will drop and this will proceed. This is for a zero order reaction where in equal intervals of time, equal amounts of the reactant is being consumed. Equal amount, okay? So here we have equal time, equal amount. This is for a zero order reaction, which we have already written. Now for a first order reaction, understand that, let's say, for some particular time t, it was reduced to 50, let's say, okay? It took t minutes to reduce the concentration, initial concentration, 100 to 50, let's say. Now, for first order reaction, you do not consider the amount, you consider the percentage. I repeat, here, in equal intervals of time, there is a drop of equal percentages of the reactant. Which means from 100 to 50, how much percentage is reduced? 50% is reduced, correct? In the same time interval, if you look at the system, from 50, it will reduce the 50% of 50. 50% of 50, which means it will become 25. Now in the next t interval, again, 50% is reduced, not the amount. Please understand the difference. It's not the amount, it's the percentage. So 50% of 25 is 12.5. 12.5 will be reduced and what is remaining? 12.5. Again, 50% reduced, 6.25, etc. And it goes on. So please note down, for a first order reaction, equal percentages of reactant is consumed in equal intervals of time. Equal intervals of time. Pay attention, it's equal percentages. Percentages. For a first order reaction. While for a zero order reaction, it was equal amounts. Both are different, okay? So based on this, there's a very important equation. Now let's say that I started with a concentration, initial concentration of A0, okay? This is my initial concentration of the reactant. This is my initial concentration of reactant. And I know that for 50% reduction or at t half, 50% is reduced and I get A0 by 2. Correct. A0 by 2. In the next t half, again 50% of A0 by 2 will be reduced. And what you get is A0 by 4. Correct? Half of 1 by 2 is 1 by 4. That is what you get. Next, what you get is again in the next t half, it becomes A0 by 8. And it goes on. In the next t half, it becomes A0 by 16. So these are all same percentages of drops. 50% of the reactant has been consumed. Okay. So there was a question in one among the competitive exams where they ask the concentration of the reactant which is left after n half-lives. I'll explain. After, for example, over here, Here, after the first half-life, you have initial concentration by 2. Okay, so this is the second one. After the second half-life, what I have is A0 by 2 to the power 2. Correct? 4 can be written as 2 to the power 2. After the third half-life, what I have is A0 by 2 to the power 3. After the fourth, what amount of concentration is left? A0 by 2 to the power 4. Or in general, what I can write is, for a first order reaction, concentration of the reactant after n half-lives is equal to initial concentration by 2 to the power n. Okay, if they ask 32, then the concentration left after 32 half-lives would be A naught by 2 to the power 32. Okay. Understand that this is not only applicable to T half, any time interval, okay? Any time interval, let it be T quarter, whatever it is, T 10%, T 30%, whatever it is, equal percentages of the reactant will be consumed in equal intervals of time. If you have half-life relation like this, then you can use this equation. That's it. Then you can use this equation. Take down a question. Question number 19. Question number 19. Two substances A and B are present such that A equal to 4B and T half of A is equal to 5 minutes, comma, T half of B is equal to 15 minutes. If they start decaying at the same time following first order kinetics, how much time later will the concentration of both of them be the same? This question can be done using integrated rate equations as well, but then I'll be solving it using the trick what I have said over here. That is equal percentages of the reactant reduced in equal time intervals. So that is what I'm going to opt over here. Okay, if you want, you can do it using integrated rate equations as well. It's okay. We have to get the final answer, that's all. Options, 5 minutes, 10 minutes, 15 minutes, 20 minutes. Okay. So let's start with what is given in the question. Read the question very well. What is given? There are two substances out of which the concentration of A is 4 times that of B. Now, we don't know the concentration, just assume it to be 100, 410, whatever it is, okay? So let's say that I take my concentration of B is 10 units, 10 molar, okay? And A will be 4 times of B, which means it will be 40 molar, 40 units. Okay. This is just an assumption because they have not given a particular value. So we can assume if you want 100 and 400, you can take that. If you want 200 and 800, you take that. No problem. Okay. Now it's given that T half of A is equal to 5 minutes, which means A, T half. T half means how much percentage will be reduced? 50% will be reduced, correct? So for A, after 5 minutes, it was 40, 50% will be reduced and it will reach 20 units. Whereas for B, if you can see, the T half is 15 minutes, which means B will take 15 minutes. Again, T half is given, which means 50% reduction. So for 50% reduction to happen, it will take 15 minutes. B was 10 initially. After 50% of reduction, how much will be formed? 5. Correct? But A is still at 20. So let's take it further. In the next 5 minutes, what will happen? A is now at 20. There will be again a drop of 50%, which means half will be reduced. It will reach 10. In the next 5 minutes, again 50% will be reduced. 50% of 10 is 5. What will be left? 5. What is the question? How much time later will the concentration of both of them be the same? A has also reached 5 units. B has also reached 5 units. 5 molar, whatever units are. Okay. So how much time did it take? For A, 5 plus 5 plus 5, 15. B, within 15 minutes, because that was the T half, it reached to the concentration of 5 molar. So the correct answer to this option is option C. You can get questions of this sort as well. Okay, so if you know this trick, things will be better. Okay. Okay. We'll move to the second order kinetics. Please write down the heading. Kinetics of second order reactions. Kinetics of second order reactions. By now, you're well at grasping the equations, integrating it, interpreting the graphs, etc., etc. Okay, so let's do it quickly. Very easy. Let's say that you have A which becomes P. Initially, you will have only the reactant whose concentration is going to be A naught. There won't be any product which is being formed. And at some time T, X amount will be reacted and that X amount will appear as well. Correct? So the final concentration of A at any time T is going to be initial concentration minus X. This concept should be clear to you by now. Okay. Now, since this is a second order kinetics, the experimental rate R is going to be equal to rate constant into concentration of A to the power 2. While by just looking at the reaction, you can write the expression of theoretical rate as well. Theoretical rate is R is equal to minus dA by dt, which is equal to dP by dt. Correct? Now, this is also rate. This is also rate. You can take these two, equate them and integrate. That's all. So let's take them. Minus dA by dt equal to Ka squared. If I bring the A terms to the one side, it becomes minus dA by A squared is equal to K dt. I can take the negative to the other side, which means this will become negative and this will become positive. Okay. Now integrating both sides. We know time spans from 0 to t. And the concentration spans from initial concentration A0 to final concentration A. Or AT if you want. Okay. Now, what is integration of dA by A squared? Coming back to the basics, we know that integral of x to the power n dx is equal to x to the power n plus 1 by n plus 1. Okay. Here what do we have? Here we have dA by A squared. And this is in the denominator, which means I can write it as A to the power minus 2 dA. Correct? That you people know, right? 1 by x to the power n is equal to x to the power minus n. That's all. Okay. Now, if you put this rule over here, what do we get? You get concentration of A to the power minus 2 plus 1 divided by minus 2 plus 1, which is equal to minus 2 plus 1 is minus 1. Denominator is also minus 1, and I can write it as minus 1 by A. Minus 1 by A. Correct? So I'll put it over here. Minus 1 by A. We need to put the limits. Initial concentration to the final concentration is equal to minus K integral dt is T from the limits 0 to T. So let's put the limits. Upper limit minus 1 by A minus lower limit minus 1 by A naught is equal to minus Kt minus 0 is Kt. Minus into minus is plus. So this becomes 1 by A naught minus 1 by A is equal to minus Kt. Or if you want, you can take minus to the left. So this will rearrange again. 1 by A minus 1 by A naught is equal to Kt. This is the integrated rate equation for second order kinetics. Integrated rate equation for second order kinetics. Okay, it's very easy. So you need to know this. Correct? The relation between theoretical and the experimental rate. The integrated rate equation is this. Now, by this time, you know 3 equations, okay? You should not get confused between them. If you put the A and A naught in opposite positions, you will get an entirely different answer. So, if you're not good at by hearting, you should be good at derivation. You will be good at derivations only if you're strong in your basics. Okay? So, don't make it a mess. Take it slow. Understand the concepts. Take your time and keep moving. Okay, so by now we know 3 relations. For n is equal to 0. It is A naught minus A. This was equal to Kt. Correct? N is equal to 1. It was ln A naught minus A, which was equal to Kt. Now, n is equal to 2. What do we have? We have 1 by A minus 1 by A naught is equal to Kt. Okay? The summary of whatever we have learned. All right. Now calculate the time or the equation for T half. Calculate or rearrange the equation for T half. What will happen at T half? At T half, K T half, initial concentration though won't change. Final concentration will become A0 by 2. So we have to take 2 to the numerator, which means 2 minus 1 by A naught, which is again equal to 1, 1 by A naught is equal to KT half, or T half is equal to 1 by Ka naught. We have learned the equation for the T half of zero order reactions as well. This is for n is equal to 2. For n is equal to 1, what was the T half? It is 0.693 by K. For n is equal to 0, what was the equation? It was initial concentration by 2K. Okay, revise, revise, revise. Repetition is the best practice for the brain. Okay, so keep on writing. Okay, so we got the equation for T half. Can you do it for quarter life as well? Please do it for quarter life as well. Quarter life. So this is half-life. Okay, I'm not writing because by now you should know the notations, okay? Yeah, at quarter life, what will happen? Let's say it is T 1 by 4. K is equal to initial concentration won't change. Final concentration will be reduced to 1 by 4th of the initial concentration, which means this becomes A naught by 4. Correct? So this is 4 by A naught minus 1 by A naught. This is equal to K into quarter life. Or this is 3 by A naught. K comes to the left. This is quarter life expression. Okay. Don't mug up. If you know the integrated rate equation, you can derive within 4 to 5 seconds. Don't take time. Okay. So that's all. Let's draw some graphs and wind up the kinetics of second order reactions. We'll do some problems in the upcoming days. Okay. Come on. So plot the graphs for the second order kinetics corresponding to rate versus concentration, 1 by concentration versus time, and T half versus initial concentration. Come on. Pause the video. Do it on your own. Okay. So what is the equation that we'll be using to plot the first graph? R is equal to A to the power 2. This is of the form y is equal to x squared. So any graph of the form y is equal to x squared will be a parabola like this. Okay. Next. Which equation will you take? We know the integrated rate equation is 1 by A minus 1 by A naught is equal to KT. Now, my y term is 1 by A, which should be kept on the left, correct? So, this is going to be 1 by A is equal to 1 by A naught plus KT. That's it. This is my y term. This is my x term. So, this is of the form y is equal to mx plus c. Correct? So, this is going to be a straight line where the slope is k and the intercept is 1 by A naught. Easy. Last one, T half versus A naught. So we know that T half is equal to 1 by A naught into K. Yeah. Now this is our y term. This is a naught, is our x term. Understand that you cannot take it as y is equal to mx. No. Why? Because if you want to take it as y is equal to mx, it should be 1 by a. It should be 1 by a naught. That's different. If it was 1 by a naught, then this would be your x, y is t half, and your slope would be 1 by k. This is different. Okay. It's just a naught, which is in the denominator. So how will you rearrange this? You will rearrange this as t half into a naught is equal to a constant. This is of the form x into y is a constant. And this expression is corresponding to a hyperbola. This corresponds to a hyperbola like this. Understand the difference between a hyperbola and an exponential decay, please. Exponential decay starts from any point on the y-axis and then it degrades. This is not like this. XY is a hyperbola like this. Okay? Okay. Yes. So that's all for the second order kinetics. We do have time. Note down the next heading, third order kinetics. Third order kinetics. Very easy. Kinetics of third order reactions. Let's begin. So how do we start? A will give products, correct? Theoretical rate with respect to A is minus dA by dt. And I'm directly writing, okay? Because we have been doing this for 2 to 3 times. And this is equal to rate constant into concentration of A to the power 3 because it is a third order reaction. If I rearrange, minus dA by A cube is equal to K dt. If I want to integrate dA by A cube, taking my minus to the other side, integrating dt, limits are from 0 to t, concentration changes from A naught to A. Okay, till here we are good. Now, what is this? This is integral 1 by A to the power 3 dA. Or I can write it as A to the power minus 3 dA. We already know the equation. It is A to the power minus 3 plus 1 divided by minus 3 plus 1, which is equal to A to the power minus 2 by minus 2, which can be written as minus 2 by A squared. So let's write it down. Sorry. Minus 2 won't come to the numerator like this. Okay. Minus 1 by 2A squared. Sorry. Minus 1 by 2A squared. So this power, which is A to the power minus 2, upon taking it to the denominator, will become A to the power plus 2. Okay, that's all. Okay, now I have a negative over here. So minus 1 by 2A squared from lower limit to upper limit is equal to minus K into T. T minus 0 is this much. Okay. Now see, I have negative on the left, I have negative on the right. I can directly cancel them. Now let's put the limits. 1 by 2A squared minus 1 by 2a naught square is equal to kt. Equation for third order kinetics. Or 2 is common, I can take it to the other side. 1 by a squared minus 1 by a naught squared is equal to 2kt. Okay, if I have to plot a graph where 1 by a square is on y-axis and time is along x-axis, how will it look? How will it look? So I'll keep this as my y fragment. 1 by a square is equal to 2kt plus 1 by a naught square. Correct? So this is my y, this is my x. So I'm going to get a straight line whose slope is 2k and intercept is 1 by a naught square. Correct? Next one, calculate t half. From this equation, please calculate t half, half-life. Half-life for a third order reaction was asked, okay, in June 2016. It was asked. Very easy if you know the equation, correct? How to do that? Our final concentration will become A naught by 2 to the square minus this is A naught. This is equal to 2k t half. Correct? So 2 squared is 4. We have a square over here. 2 squared is 4. It will come to the numerator. 4 minus 1 is 3. So we have 3 by A naught square is equal to 2k t half. And if I rearrange in terms of t half, this is going to be equal to 3 by 2k A naught square. This is the expression for t half. Very easy. Very, very easy. Plot a graph, please. What if I have to draw or plot a graph between t half versus 1 by A naught squared? So, t half is y. 1 by A naught square is x. So this is of the form y is equal to mx. There is no intercept. It's going to be a straight line passing through origin and the slope is going to be 3 by 2k. Easy. But if the question is to plot t half versus, let's say, 1 by initial concentration, not 1 by a squared, 1 by a, then how will the plot look like? How will the plot look like? Understand that now this is t half, which is y, and our x element is only 1 by a naught. But here what you have is 1 by a naught square. So what you have over here is some constant into x square is equal to y. This is like y is equal to x square's variation. We already saw if you have y is equal to x square, it's going to be a parabola. Going to be a parabola. One more variation. It's going to be very easy if you are thorough with the graphs, okay? Let's say you have T half versus A naught square. So what was our equation? It was 3 by 2k. Instead of A naught square, you can write it as x square. This is equal to y. Or if I rearrange, I can write it as x square y is equal to a constant. In second order kinetics, we saw xy is equal to constant. In third order kinetics, we are seeing x square y is equal to a constant. Both of these are hyperbolars. Okay, it will be slightly deeper, that's all. That's it. Okay, so I had covered this in the basics as well. If you have a graph and if it looks like this, let's say this is xy is equal to a constant. If it is slightly deeper, like this, like this will be x squared y is equal to a constant, or xy square is equal to a constant. Okay. All right. So with that, we have completed our kinetics of second and third order reactions. Okay. Now there is just one more lecture left for completing part 1. And that's going to be the kinetics of nth order reaction. Very easy. You will get a general formula. And we'll also learn about pseudo order reactions. And with that, we are going to complete our first part. Okay. So that's all for today. No homework questions. We'll do 4 to 5 questions in the next class. And with that, we'll wind up and we'll start doing assignments. Okay. Okay. So that's all for now. Thank you.